Sweet.
Richard. All right, here we are.
Cool. All right. Well, welcome everyone. Let's just kick it off. Figured maybe we could just go with some quick intros first. My name is Russell. I'm the head of Nucleus at Scale. Used to do research with Andre, Justin, Richard at the Stanford Vision Lab. Do some work on the autopilot team at Tesla, and excited to chat about some recent breakthroughs in AI with you all.
Awesome. Stoked to be here.
Cool. Richard, you want a quick intro?
Sure. Hi, everyone. My name is Richard Socher. I am currently the CEO of U.com. It's a new search engine. Russell, I think we get some feedback from you. I'm the CEO at U.com, a new search engine. We haven't launched yet. Going to launch in the summer. Before that, I was the chief scientist at Salesforce and EVP there, leading a research team of a lot of AI folks. And before that, I was the CEO of MetaMind, an AI platform company, and an adjunct professor at Stanford, where I was teaching deep learning and NLP. And before that, I did my PhD at Stanford on deep learning for NLP and vision. That's me. All right, over to you, Andre.
Yeah, sure. I guess I'm Andre. All of us overlapped at Stanford during good PhD times. And I'm now at Tesla working on the autopilot and neural networks for it.
Yeah, then I'm Justin. I overlapped with all these guys at Stanford. I'm now an assistant professor at the University of Michigan, and I also spend part of my time at Facebook AI Research.
Cool. So I think we wanted to mostly keep it pretty flexible today, but maybe start by talking about some of the more interesting recent breakthroughs in multimodal learning and kind of image text learning jointly together. So I wanted to kick off things talking about kind of Clip and DALL-E. And curious for your guys' take on what do you think is the most significant part of those works? Like where is the breakthrough, and is it a breakthrough?
Okay, a loaded question. Also, how recent of papers are we talking about? So we just discovered actually 5 minutes ago that there's a brand new paper that follows up on Clip that showed up in the archive today. Yeah, from Google.
I guess it's from the group at Google.
None of us has read this paper yet, right? So it's going to be hard to discuss when this just appeared.
That's the magic. We need some more archive sanity, Andre.
Archive sanity is almost always offline. I get a tweet every third day to restart the server. It's kind of but I'm on it. I guess to answer the question, so I really, really liked Clip. When it came out on the same day as DALL-E. And I think DALL-E got a bit more attention, but Clip was sort of like the very thorough release with a paper and a code that came out. And it was, of course, quite exciting for me to see. Actually, my PhD is connecting images and natural language. Like that's the title of it. So Clip is like exactly that. And of course, all of us have worked on images and language quite a bit. Justin and I at Stanford, and Richard even before then. So this is a topic that's like dear to our heart. And Clip, of course, had like some pretty amazing results in it, and DALL-E as well. So I was pretty excited about that.
Yeah, and maybe for the folks who here aren't familiar with, so Clip basically allows you to classify a lot of different visual categories, and you don't need to have a specific training set for a massive amount of them. In fact, I think like million plus different labels, and they train on a massive data set. And this is kind of, I think, now a pattern with OpenAI. They really take some of these existing ideas, and I think Ilya used to say minimum innovation for maximum impact, and it's working really well. Like you take the existing models, but you scale them up so massively, and you realize, wow, there's still so much potential for AI in just that idea. In fact, the last couple of years, one might argue that not that many new research ideas have actually happened that were truly transformational, and we're still using ideas from the last like maybe 10 years plus ago of take a very large general function approximator, usually some kind of neural network we can train, take a massive, large data set and then combine the two and fiddle around a lot with training and hyperparameters and eventually and optimization techniques. And then you can do some incredible things. And that is really, that those kinds of ideas have really been the mainstay of a lot of the different AI breakthroughs of recent years. And it's incredible how much longer we can push on that. And it's kind of a question too, what might be next once we have sort of worked on all the problems that really you can create gigantic training data sets for, and how far we want to push training these massively large models. Because at some point, you may have this massive model, but the hardware hasn't fully caught up yet, despite TPUs and so on that aren't like freely available for as many people to have in their homes to be useful innovations in that sense.
Yeah, so what I like about Clip is not so much the scale. It's maybe let's back up and describe what this thing actually is, right? So Clip is a method for training visual representations from language. So what are visual representations? In computer vision, we're always training big COMNETs that input an image and then output a bunch of numbers spit out by the network that describes some content of the image. So the kind of way that we usually do vision these days is you get a big data set of images and labels, usually labels of like image paired with dog label or cat label, or just a label telling you what's in the image. Then you train a big neural network that inputs the image and then tries to predict the label that a person said was in the image. And that's kind of the formula for training convolutional networks that has really kicked off this whole deep learning revolution back in 2012 with ImageNet and AlexNet. And that works really well. That's supervised learning, where you take an image and you have a human specified label and you predict what the human says should be the label. That's great. But of course, the problem is that labels are expensive, and asking humans to label giant data sets is time consuming and annoying and painful. So people have been trying to figure out ways to get away from supervised learning for a long time. And there's been actually a lot of progress on that too in recent years, where methods like Moco, SimClear, SimSciam, Bootstrap Your Own Latent, and other friends like that are now able to input a ton of unlabeled images, mix them all up in a soup with contrastive learning and other types of fancy unsupervised objectives, and then learn convolutional networks that give good image features even without any human specified labels. So then we've got supervised learning like ImageNet, we've got unsupervised learning like SimClear, contrastive stuff, but now Clip is something a little bit different, because Clip is kind of supervised. It's still paired data. Their data set is now pairs of images and language. And the language was written by people and pulled off the internet. And now you want to try to learn a network that tells when an image is associated with a piece of language and tells when a piece of language is associated with the image. And in doing that, you end up learning a really good representation for language and a really good representation for images. So now this is nice because it's scalable. We can collect a lot of data by scraping it from the web, but it's also practical, right? This unsupervised learning problem of learning from images only, it's kind of like an academic exercise, in my opinion, right? Like anytime you get images in the wild, they're always going to be accompanied with something. And Clip is a nice way to use that something to get really good visual features. And that's what I like about it.
Yeah, and it's actually worth also pointing out that this has been around, like the idea roughly has been around for a long time. Like Richard, you have a paper where you're from a way back when, where you're using contrastive losses to basically bridge images in natural language. Like this has been around for a while. So really what has changed is just mostly like the encoders and the architectures. And mainly it's, we're using a transformer now instead of, whatever else was there at the time.
That's right. Yeah. I mean, and in their like they cited the paper, one of the first sort of few zero-shot learning papers where we just mapped single images and single words from like together into the same vector space. But it's just exciting to see that we can train these massive models now and found ways, and in some ways people say, oh, it's like exactly the same of what it's been for many years, but really people haven't been able to like train these models even if they had better compute. Like there are some novelties on the optimization and regularization side also.
Yeah, but
the big difference. Yeah. The big difference with a lot of this earlier work is that it doesn't rely on everything is trained from scratch. And that's the major difference here. And a lot of this earlier work that was that we were doing during our PhDs, you always start by training the ComNet on ImageNet. And then after that, you use that ComNet for something else. And Clip is inverting that they're training everything from scratch, and they're having vision and language as the primary pre-training task. And then all the visual recognition tasks are actually downstream from vision and language. And that's actually flipping things completely on their head from how vision and language was done just a few years ago.
And the only reason you can afford to do that, by the way, is because they have collected this massive amount of training data that allows you to actually train this. So to me, this was probably the most surprising part of the paper, to be honest, is that they found a way to somehow scrape 400 million pairs of images and text. That to me was probably the most surprising part, and intuitively the part that probably makes it work so well.
Yeah, that seems like the difference between a lot of the kind of academic work in the past and what's really showing progress now, right? Which is that we actually can, train on data of that scale. I think the hardware improvements that we're seeing are a really big part of why all this is working today, right? Like, it's not just the next generation of GPUs, it's the interconnect, it's the software to support large scale distributed training. I think all that plays a big role in getting to where we are.
For sure. Yeah, it's interesting that machine learning tooling is becoming more and more of a VC category, and folks are really doubling down because there's just enough demand that companies like Hugging Face and Weights and Biases and so on are doing incredibly well, because they're making it more convenient to train your own model. But people still want to train their own models.
Mm-hmm. So what is it? Go ahead.
I predict there will be more and more tooling to make this more convenient. Like Andrej talked about software 2.0, where we program less the machines and more about the data. And so, well, if that means, you have to collect the data, you have to label it, you have to clean it. And of course, Russell works at scale, that labeled data for others. I think we'll see a lot more tooling around this new software stack in the next couple of years to make this easier and easier for people.
Yeah, I think what we've seen, at least at scale, is that increasingly the investment from companies is not, obviously folks are getting more data and getting more compute and working on models, but it's really the infrastructure, where the infrastructure is kind of the most compounding return in a professional, kind of like production machine learning setting, where you can kind of try new experiments and get better accuracy, but to actually increase the rate of innovation, it mostly comes down to how good your infrastructure is.
I think that's true even in academic settings, right? Like, a lot of students, they just want to load things up, train their models, and not be very careful with what experiments they're doing and when. And whether you're in production and trying to improve things out in the world, or whether you're trying to invent new techniques in the university, just carefully controlling the infrastructure, keeping track of the experiments you run, what works and what doesn't, is always important.
I guess I'm curious. Okay, go ahead, Russell.
No, you go.
I guess I was just curious of people's reaction when they read Clip, since we talked about it briefly. I guess my reaction when I first read the paper, when I saw it, was number one, I'm really glad that people are looking into this, because to me, natural language is like this ideal label space. I don't want to have, on ImageNet, we have 1,000 categories and we call them piano and dog and so on. But then those labels are really just for us. For the neural net, it's just a bunch of 1,000 random categories, right? So I really love that we are using natural language as a label space. Second, it's very practical because you get all this free supervision from the internet if you can scrape it, and it turns out that you can. So when I read the paper, I was immediately shocked that 400 million and that they were able to collect this. That was great. And then of course, all the other experiments were very nice, showing that the representation that you get on learning from this rich domain on this data set gives a much better, potentially, ComNet for fine-tuning on many other diverse number of tasks. And so does this replace ImageNet fine-tuning? ImageNet pre-training? Because everyone is using these ImageNet pre-training ComNets. Should they be using this ComNet instead? And the last thing that I really, really liked, and this was a trend over the entire 2020, was that, of course, there are transformers at the heart of the architectures for both processing the text and the image. And transformer is a massive I mean, it's just a massive trend of 2020, and it's incredible to me just how far it's gone and all the places it's it's going and replacing all the traditional architectures. And so I also loved to see that in the paper, and that OpenAI is basically using like a single code base in my mind, almost like they have this single transformer code base, and they're just making it do a lot of things. GPT, image GPT, Clip, DALL-E, and you're just like restructuring what the indices are, but you're still fundamentally just like modeling sequences of integers, and you are just changing the schema of what those integers mean. And you can do so much stuff with just that. So that's what
One thing I find fascinating about the transformer architecture is how much our compute and hardware paradigms right now influence our modeling. A lot of times people like to think like, oh, I work on the modeling. Oh, I don't want to do this like hardcore C++, like CUDA kernel coding type stuff. I just want to work on these beautiful mathematical models. But really, the main breakthroughs like transformers, they became breakthroughs because they're so highly evolved in our current hardware, GPU, lots of small parallel processing kinds of paradigms, and that's something that a lot of people don't like to admit, because what other architectures might we come up with if we had different computing hardware architectures below it. So that's one thought, and then to me, I think the interesting bit on the modeling side in these tasks is that the task formulation is so crucial. Namely, that this is kind of a massive task that is so hard that it's essentially impossible in the limit to fully learn everything. It's similar to language modeling. Language modeling is essentially a massive multitask problem in the sense that you have thousands and thousands of words. And if you want to be able to predict the word that comes next, which is, what GPT-3 on a simple level like does as its objective, in the limit, you have to have all of human knowledge and logic and math and so on. If I, tell you like the solution of 25 times 3074 equals like something, then that number, in order to be able to predict that those next couple of words, you need to be able to do math and so on. And so I think the trick is, how can we use this idea of multitask learning to have a single model that just keeps getting smarter and smarter? And where I would like to see the AI community get to is to not just share some open source code or some pre-trained models, but to start sharing a substrate, a neural substrate, some kind of very large general function approximator, likely a transformer right now, and then actually continue training that one model to get better and better over time at more and more different tasks. And if we stopped sort of restarting all our AI projects one at a time, and instead are agglomerative, cumulative, similarly in a similar way as we are with intellectual ideas and papers, but actually we're doing that in the actual model, I think the community will be sort of supercharged and make even more progress and have even more amazing zero-shot capabilities in the next couple of years.
Yeah, I think that's a great point. I think, first of all, just on the hardware side, what I've seen is that a lot of the most impactful research is done by folks who are deeply appreciating not just the mathematical algorithmic side, but also, what's possible to get maximum efficiency out of the hardware today, right? Where you're seeing, I think this with transformers in particular, there's this term introduced by Sarah Hooker recently, the hardware lottery, describing, this observation that when a certain research direction happens to align well with what's efficient to do in modern machine learning hardware, then the gap between that research directions and others can accelerate, because you're going to get better and better results kind of optimizing further and further for the existing hardware. And I think it's true. And in that sense, it was framed a little bit as, maybe these research directions aren't necessarily superior. They're just kind of better suited for our hardware today. But in some sense, if that's what we have, then that might be the fastest way to make progress, at least in the near term. There's like one paper I really liked on this. It was not a fundamental breakthrough, but a really elegant example of a researcher understanding kind of the full stack of hardware to software to algorithms. Was this paper that looked at how most convnets are implemented and realized that the convolutional layer is typically implemented as its own layer in PyTorch or TensorFlow or have you. And then the batch normalization layer comes after and is also implemented as its own layer. And that under the hood, what has to happen is you have to kind of move data in and out of cache lines on a GPU into memory to do that whole convolution, kind of compute those the convolutional dot products essentially, and then do kind of put it all back and then go fetch it again when you're doing your batch norm. And if you actually kind of write a layer to fuse that and just do it all at once, due to the underlying hardware implementation, it can be a lot more efficient. And so that's one small example, but I think there's a lot of opportunity for folks to kind of build the next generation of algorithms, with the hardware fully in mind. And then the last point I wanted to touch on was, Andrej's observation that, 2020 was really the years of the transformer. And so I guess I want to ask the group, to what degree do we expect this trend to continue? Are ConvNets going to be deprecated at some point? Are we all going to be using, image transformers for our large scale neural networks that we continuously fine tune and never train from scratch again?
Everything will be deprecated at some point. I'm sure we'll come up with new architectures. What I'm actually interested, I almost am less surprised. Honestly, I think the space of models that we have explored is tiny. And my strong hypothesis is that there'll be thousands of very similar different architectures. And the main thing that we want them to do is that they're trainable with some ideally asynchronous SGD, that they're highly parallelizable because of the current hardware architecture, and more abstractly, that whatever architecture is currently fast in the hardware side, they can be trainable on that architecture. And then as long as they're general function approximators, it almost doesn't matter anymore what kind of model we'll use. I think the bigger question in the future, and in some ways we're hinting at this here too with these, is what are the interesting objective functions that we are still coming up with? And then to go even further into the future, how can we actually eventually conceive of models that will come up with their own objective functions? And that to me will be sort of where AI can make its next big breakthroughs, that are sort of, once we've exhausted we take a massive model and train it on massive data sets with a very large, in a very large setting.
Justin, what do you think about the clip?
Yeah, I think I've been a little bit more down in the trenches on this kind of stuff than some of these guys. So I had a very different reaction when I read clip, because I've been actually working on some very similar stuff with some of my students at the University of Michigan. So we had a paper called Vertex that came out sometime early 2020. That was basically the same pitch, that you can take images, you can take text, you can train a really good image features from scratch with a bunch of images and text. So on the one hand, I was really excited to see this idea getting picked up by OpenAI. But on the other hand, I was terrified that now my students in my academic group would be having to compete with this giant, well-funded OpenAI lab. So it was a little bit vindicating that I was on the right track, but also terrifying.
Mm-hmm. And there are some details that are different. Like, for example, you guys used a generation, basically not a contrastive learning. And that actually ends up making a difference, right? Or at least it's argued in clip that does.
Yeah, exactly. So in our setup, we had a model that inputs the image, and then the image goes through a CNN, and then from the output of the CNN, we then spit it to a transformer that tries to generate the language. And Clip is using a matching objective instead. So they have and they did some experiments with our kind of autoregressive setup, and they found that the contrastive setting was working a bit better, which we actually tried a little bit at first, but maybe we got the hyperparameters wrong at first, and autoregressive seemed better for us at the beginning.
Yeah, it's interesting. There's different ways you can pose this. Basically, you can go, you can predict text forward, you can predict it backward, you can do it both ways. You can do masked learning, or you can do contrastive learning. It seems like everyone has explored everything, but the hyperparameters actually really matter.
True that.
So how do you deal with that as in, kind of leading a lab, Justin, when OpenAI starts to work on, similar research with much more computational budget? Like, what is the role of academic labs in this research direction, given how big the computational needs are?
Well, your goal is not to try to beat them at their own game, right? Like, we don't have as many GPUs at Michigan as they do at OpenAI, and we just can't try to beat them at that game. But there's a lot of games to play, right? Like, there's more to research than just getting the biggest numbers and the biggest data sets. So like Richard was saying, part of the innovation that is going to drive us in the future is what are the objectives that we should be training for? What are the tasks that we should be addressing? And those types of questions are the role of academia, to try to think of what are the things that are not super scalable or super practical right now, but might be just over the horizon and help open up these big breakthroughs a few years down the road.
Yeah. And maybe on that front, I guess somewhat shameless plug on the two things that I was most excited about at Salesforce Research when I was still there and still am and helping them still right now is the Ai Economist, where instead of playing games, you create a simulation and then you can test out millions of years of taxations and millions of different forms of taxation, and then come up with the taxation scheme that leads the most in a certain metric you want to optimize. In our case, we decided productivity times equality, measured by 1 minus the Gini coefficient, seems like a reasonable objective that a lot of people could agree on, but you can add other objectives like sustainability or whatever you want in there, and then actually have an AI that tries to optimize something new. So I think there's still a lot of space for academia and industrial research labs and really everyone to make impact of bringing AI into new areas that haven't been as explored. And another one is in protein modeling, where we use similar ideas to GPT-3 in language modeling, but on the language of proteins and amino acids, and then trying to generate new kinds of proteins. And there's a ton of exciting stuff that we're working on there with real wet labs now, where I think you often know that you're onto something interesting in AI if you're also in the process creating a new unique data set. And that data set is really hard to create. Like when we started creating ImageNet back in the day in Feifei's lab, like that was a lot of work. Like Li Deng was a systems PhD back then, and he spent years trying to scale up that system to create that really unique data set. And you kind of know that, man, if this is an area that people care about and you're creating this unique data asset, you're probably onto something in your research. And that can be like new complete areas. Like economics has, despite how important it is, had surprisingly been little impacted very not very much by AI, which is kind of surprising.
Poor Deng Jia, actually, when he was constructing ImageNet, he actually sat next to me for a while in his lab, and he was not enjoying it, but he ended up having a huge amount of impact, of course, with that work.
Right. Sorry, did I say Li Deng? I mean Deng Jia. Yeah, of course.
Sorry.
Yeah, it's very impressive, and he's had a lot of impact. And similarly, Alex Kruszewski had a lot of impact with hardcore engineering of CUDA kernels and such. So it's like something that I have to tell a lot of aspiring and young AI researchers. They're always like, "Oh, I want to work on this cool new model." And like, some people have innovation there, right? Batch norm, that paper has a lot of citations and it's like a clever, neat, like algorithmic idea. But a lot of the really impactful papers, there's something painful on the algorithmic, on the coding side and engineering side of things, or the data collection side of things.
Yeah, like a lot of the innovations have been around data. Like, in machine learning, you'd think people had learned this idea by now that data is king, but it seems that people still don't get it. And like even in the CLIP paper, like to me, one of the most important things there is the data set. They've got this new data set of 400 million images and text, and they spend like 3 paragraphs in the paper discussing how they collected it and what's in it. And to me, that's maybe the most important and interesting part of the paper.
Yeah, it's true. I actually struggle with this quite a bit because whenever people join the team at Tesla, the neural networks team, their instinct is always to start going crazy on the architecture, and I have to unlearn that for them. I have
That's
to,
right.
they have to iterate on their data set, and it's like eating their vegetables, but it's so incredibly important. But
yeah, it seems like in academia, most of the time you're stuck with the static data set because that's the comparable benchmark, right? And so it's either a ton of work to create your own data set from scratch, or you just use something off the shelf so you can compare your work to others. And like Justin, you created your own data set from scratch, the kind of clever data set, which really I think was an interesting way of exploring this combinatorial explosion reasoning problems that can happen, and whether language models are pattern matching or actually learning to be able to listen to commands, which you could talk about. I think is super interesting. But like I remember you had to spend a ton of time just like on the rendering library, making sure that the reflections didn't have artifacts, and it was a huge grind.
I mean, yeah, it's a grind, but I don't think it's eating your vegetables. I think making new data sets is maybe the most fun part, because if you want to get an AI system to do something cool, then all you need to do is get data of that form. And this is a pattern that we repeated in tons and tons of papers. Like when Andre and I did this paper on dense captioning back in grad school, we built this system that's jointly detecting objects and then describing them in natural language. And that was a thing that nobody had ever done before. But the thing that enabled that is that we collected a new data set of data of that type. And that's been a trick I've used on tons of projects. It's just you want to have a system that does something cool. So you create a data set that has that cool data, and then that lets your system do something new.
That's right.
One small example of this is actually this project that I worked on with Richard, where kind of going back to this idea of multimodal embeddings between languages and images, we were trying to improve the state of the art for the reinforcement learning environment, Montezuma's Revenge. And for those who are unfamiliar, Montezuma's Revenge is maybe one of the hardest Atari games out there, because basically anything you do, unless it's exactly right, you die. And so it just takes a machine learning agent tons of time exploring the environment before you're going to get any reward signal whatsoever, because you'll just most likely die halfway through. And so we were looking at this data set, figuring it's so frustrating, because you kind of just want to just tell the agent, hey, you have to jump over the wall first. But there's no way to communicate that unless you have this actual prior that lets you basically, if you want to speak in natural language to an agent, you need to have that multimodal embedding space where those commands can actually be translated. And so, yeah, with Richard, we kind of made a very small scale version of this and showed that if you then do that up front, you do that work up front, you can give instructions in English to an RL agent, and then from there really accelerate conversions. But the work is in the data set preparation.
That's really cool. I mean, that must be the future. It's just like giving instructions to massive models in English. That must be the future. And GPT is really the first model that sort of like demonstrated that working.
I'm excited about that future too. Is there any chance we can take audience questions too on this?
Yeah. We absolutely can. I think there are some. Andre, were you going to say something first?
Well, yeah, I was pretty excited to talk about Clip. I guess we've like covered that. I'm also really curious about your guys' thoughts about DALL-E, because they sort of like came out at the same time. They're similar. So yeah, I was eager to talk about that, but we can also take a few questions.
All right. While I add someone, maybe someone can answer some thoughts on DALL-E first.
Yeah, so DALL-E is this kind of counterpart to Clip. So Clip is sort of matching up images and language, and DALL-E is taking language as input and then generating an image as output. So I kind of felt a sigh of relief when I saw that paper, because I had started building a reading list a couple months ago about trying to do a project like that. I thought like, hey, nobody's done a big text to image project with transformers yet. Maybe I could get that one done. So I started drawing up a reading list and was thinking about trying to find some students to work on that. But then other projects got in the way. And when I saw that OpenAI did this project, it was like, oh, great, that's one that I don't have to do.
So actually, it's really funny because when we okay, cool.
Anand, did you have a question?
Hey guys, thanks for bringing me on. Quick question. I know 2020 was the year of the transformers. We use a lot of transformers, especially for our cars. One of the conversations that you guys sparked up was, would transformers eventually overtake CNNs and replace them? Super curious to bring up that conversation again. Any thoughts on that would be awesome. Thank you.
So yeah, I'm super interested to talk about transformers as well, just because I mean, so I just feel like there's been this arc of development. Like when I started my PhD, what's incredible to me is that there were all these different areas of AI, right? Like there were natural language processing, there was computer vision, there's speech recognition. All these different areas had all of their different papers, and you couldn't really just like read the papers from a different area. You worked on computer vision, and it had its own language, its own, literature, and so on. And what we've seen is just this like massive consolidation over time. So natural language and speech and all the other areas sort of started to use all the same tools, the neural network specifically, but the neural network looked different. So, you know, someone was using COMNETs, someone was using recurrent nets and LSTMs, you know, or, you know, other flavors of neural nets, I suppose. But everything started to look somewhat similar in the sense that you just have data sets and you train with stochastic gradient descent, backpropagation, and so on, and you don't engineer these features. And I think transformers are just another step of this consolidation where it's incredible to me that you can now just literally cut and paste the same 300 lines of PyTorch defining your transformer, and you can just literally copy paste that across like lots of different domains and gets basically state-of-the-art results. So I just think it's another step of this consolidation. And now the architecture is the same. So now what changes between different areas of AI? Like not much. The data set that you feed it. So that's what I really like about transformers, is that they're extremely good, and they free you from this burden of space in computer vision. In computer vision, your COMNETs are defined sort of in three-dimensional space, and that's how you lay out the computation. But in transformers, everything is sort of like you know, graph-based with positional encodings, and so it's an extremely flexible architecture. You can very easily plug stuff in anywhere and really lay it out in whatever way you like. So I am definitely in love with transformers.
I think they're great too. I think my strong hope is that we can move to more multitask learning. And I think, to me, they're like the greatest substrate we have right now towards that. And the trick, there's still a data set and a benchmark in NLP, namely the natural language processing, the Decathlon, Deca NLP, that nobody has yet been able to get better numbers on. And it's kind of surprising given all the advances we've seen, but it's really still hard to create a single NLP model for all the different NLP tasks, like summarization. One sort of secret here that we don't talk about very much is that none of these AI models can really, on a reasonable time frame, read a book or read any text that is really, really long and keep most of the facts of that text in a discrete, concrete memory, and then reason over it logically. So there's no good book summarization, for instance, model. And it's kind of embarrassing. Like all the contexts in which these models tend to work in is a few hundred words. And once you want to generate something that's much, much longer than that, because of the limited context, they will tend to repeat themselves and things like that. So I think there's still work that needs to get done on these models. And I guess right now, you know, the transformer kind of scales quadratically by default in its input length, and so it's maybe not the best model for the next couple of years or decades, because ideally you can have a model that continues to learn and has a much, much longer window that it can attend over than standard transformers. So they're awesome right now. They're great for shorter texts and amazing for images. But if you want to work in longer texts and translate a whole book such that consistently in each chapter, between different chapters, it will use similar kinds of translations, or trying to create a complex summary of a long, complex history or story, or a news, sequence of news articles that is consistent and doesn't repeat itself and remembers what has happened before, and so on. I think we do need to innovate on models that will scale to these kind of longer inputs still. And part of that, even in NLP, we see some models do really well in sort of statistical things, but still struggle with some logical things as they get more and more complex. Even simple things like multiplication, if you talk it out, these models have seen enough, they memorized enough, but eventually the numbers get too large and they still can't multiply relatively simple, integer multiplication once the numbers get too large, even though like each single word is represented as a list of 1,000+ numbers. So it's kind of embarrassing that we can't do it. So as amazing as transformers are, I don't think they'll be the final model that will get us to like a full AGI, but they're certainly like another really great step towards it.
So do you think that transformers, the kind of future there, at least I was curious with the mathematics example you brought up, because it's a great example where you can kind of squint and you can see these models starting to do basic addition, really basic arithmetic, but a few digits in, and it really breaks down. Do you think that the future of these models has kind of built-in architectural inductive biases for these common, subroutines like math, like other things? Or do you think that actually, with enough scale, we can kind of brute force our way through and that's where it's going?
I'm not sure the scale will solve that one. And at some point, sort of induction type logical inferences, like reasoning over complex sets, some of which might be finite, some of which might be infinite. Like, I think we need some different model innovations or objective function innovations to get there, is my hunch.
Yeah, but that's also where a transformer might help, right? Because the reason that something like GPT-3 could add or subtract is because it's probably seen like 1 + 1 = 2 and 2 + 2 = 4 on the web. But for really big integers, it hasn't seen those. So for humans, when we encounter big integers, we don't memorize the answer. We instead run a little algorithm to compute the answer.
Right.
But then the algorithm is a fixed thing. But a lot of those algorithms involve like I've got an array of items in front of me, and at each step of the way, I need to pick up some of them and compute with them. And that's what self-attention in a transformer lets you do. So I'd hope that they could help us learn algorithms better.
That would be cool if you had more sort of compositional reasoning from smaller subroutines that can be reused. It's something that, unfortunately, current computing architectures like GPUs and TPUs and so on aren't particularly great at. And so there's very little model innovation in that direction.
Yeah, addition is a cool example, actually. So when I was re-implementing GPT, MinGPT, one of the examples I was focusing on specifically is addition, because I was kind of really curious if you can just like crush addition specifically and just study it as a problem, like scientifically, as to whether a transformer can learn the algorithm and whether the algorithm for addition is even sort of like an element of the set of programs expressible by a transformer, which I think is true. And so I was trying to write out the transformer weights by hand to do addition. But this is kind of like 50% done. I think basically it can learn it, and it just like probably hasn't seen enough examples of it to really like develop the algorithm in the weights in a stable sort of way. So yeah.
Do we have a question from Lex?
Yeah, I think for the most part, my question was almost answered, but I wonder if you could talk about it a little bit more. Whether there's ideas outside of transformers, or whether what Andrej said with transformers learning programs is the way for lifelong learning. So for looking at book length or multiple book length inputs, is there ideas that you've seen that seem promising? And I mean, maybe staying in it longer, do you see transformers somehow being able to do that compositional reasoning, or being able to learn programs, or do that kind of thing? So I guess my question is, have you seen stuff outside of transformers that's promising for lifelong learning?
I think lifelong learning is a bigger question than transformers. I think for lifelong learning, we don't even have the right task or the right setup yet. Like, we kind of want a setup where there's data constantly streaming in and the model is sort of training forever and constantly getting better and better. And there have been a couple papers like that, but I don't think any of them have really cracked the overall task setup yet.
Right. I think there's sort of a big gap in what you may sort of loosely also allude to, the thinking fast, thinking slow kind of things, and that some tasks may require you to put things into memory, and some of that memory should stay in, some of these facts that you put into memory should stay there forever and should stay in your long-term memory, and some might only stay in a short-term memory. Like in a story, you might say, let's assume this other person won the presidency. And then, this other thing happened. Now what would happen? And then at the end of that story, you should delete that from your memory and not assume that it was the case, right? And so I think they're still, like, the ideas, some of these ideas have been around. Compositional reasoning has been around. I did a lot of that in my PhD. And some people have had sort of ideas of having a long-term memory that is kind of associative too, and you can store vectors in that and then retrieve them later. And the neural Turing machine has been able to do some things from DeepMind back in the day. Feels an eternity ago now. But I think nobody has really put it together yet and then really massively scaled it up so that you can have long and short-term memories. You have compositional sort of programming modules that learn functions like additions and then learn how to trigger them and also have them learned in an end-to-end fashion from actual observable training data. I think there are a lot of the ingredients are there, but I haven't seen anyone really put them together in an interesting new way.
Is it possible? Okay. Oh, sorry.
Can I was gonna. Oh yeah, go for it, Lex.
Just to really quickly add, is it possible, like you guys were saying earlier, that this is also a data set problem?
Partially, for sure. It's really hard to do it. But then, of course, we also know that there's some possible like evolutionary learning and sort of combining some of that to have architectures that are kind of predisposed to learning certain things that seems like most people are able to learn if given like cultural and linguistic and social contexts. And there might be some of these things might be missing, and that kind of alluded to, I think, Justin's question of maybe some of these could be given as sort of basic building blocks. But of course, it's always nicer if you had actually a data set that captured all of these different patterns and it could learn it in an end-to-end way.
I was going to say for this lifelong learning setup, I think it's kind of a data set problem and also kind of a social problem in the way we do machine learning research, right? So each paper is relatively small in machine learning, like we publish a lot, and each paper is usually introducing some new widget, and we need to prove that that widget is better than the previous thing. So it's to do those kinds of comparisons that are usually expected in publications, you need to like take the previous data set and add my widget and show I get an improvement. And if you're trying to do something much bigger, like a whole new lifelong learning paradigm, then it's really hard for me to fairly compare with anyone else. Or more importantly, then it's hard for the next person to fairly compare with me, because now they're sort of streaming and seeing totally new data when they let their system out in the wild. So I think it's almost a social problem in a way that more people aren't working on that.
So we can actually see the entirety of academia and research institutions as one algorithm that's performing lifelong learning by generating better and better architectures and better data sets. And over time, we'll solve the problem of AGI. So if we look from that perspective.
It'll be multiple lifelongs, yeah.
What I want to see in academia is there's all these competitions, all these benchmarks for, all right, here's the data set. How good can you make your model? But what I think one thing that's really missing, like based on this conversation, is where's the competition that says, hey, here's the model you have to use. How good can you make the data set? And how can you actually encourage research in the infrastructure and kind of machine learning enabled engineering to construct really high quality data sets to actually solve practical problems?
I mean, this is what I was referring to and trying to get this one single substrate, a single model, and then have everyone try to add new objective functions to it such that you don't forget previous tasks and it keeps learning new tasks. Like people learn new tasks without necessarily forgetting all their old tasks. Sometimes there is, catastrophic forgetting and interference or like mild interference, but you often can bring that knowledge back fairly quickly. And that to me is like the lifelong learning question too. And multitask learning is kind of step one to lifelong learning. And I think there's still, we still need to have some novelty on the optimization side and regularization side and memory side to keep knowledge around and knowing what things to update, how to basically share some of the weights in a neural network to update based on a new task, and which weights are not relevant for this task and should not be touched as much, and you should not catastrophically interfere with them so that you keep around the previously learned skills. I think multitask learning is the next big barrier towards lifelong learning.
Do we have a question from Maria?
Sure, yeah. I was going to take things back to the few-shot, zero-shot learning scenario, given that we're talking about transformers. So I know that it's been demonstrated that scaling language models up improves few-shot performance, and that tends to be task agnostic. I was wondering what folks think about the potential for transformers in that space and what future areas of research are, especially in vision tasks, not only NLP.
Yeah, I think that kind of brings us back to CLIP, and because CLIP was one of these ones that was able to show some really cool zero-shot and few-shot performance for vision tasks, and it has this right? Because then now you can program your classifier via your visual classifier via language. So I think Clip was the first one to me that got that to work in any way, and I think we'll see a lot more going forward there.
Yeah, I definitely would echo that. It's basically like the insight is that you are using natural language as this domain for transfer instead of these arbitrary categories that any different data set may define. And this allows you to also collect nearly infinite data. It's kind of unfortunate, almost like in AI, just how constrained we are by the data that you have available to you. And it really constrains like what these algorithms or like what these models are allowed to do almost. So maybe like Richard, for example, you mentioned briefly summarization. Like one of the reasons we may not have really good summarization is just because, you know, where's your data set of 100 million summarized, you know, examples. And so almost like the forms of data that you can naturally mine in the world kind of like constrains what you can even explore, which is kind of annoying.
I agree. And what's interesting there is it's not just like the data set as is, it's actually rethinking data sets and maybe combining them with simulations and moving away from the purely supervised kind of thinking of data sets. And even, you know, language models, technically it's sort of this weird unsupervised/supervised. It's unsupervised in the sense that no human had to sit there for this particular project and label data, but it's supervised in the sense that humans actually, you know, wrote down all of that text. And it's supervised also in the sense that you basically make it a supervised prediction problem by saying, given the last 99 words, predict the 100th word. And then, you know, you move that window and that sort of supervised label block one to the right in your Wikipedia text or a larger like internet text. And so I think one interesting future may have to move beyond that paradigm. And so, for instance, summarization is actually a problem that is under constrained the way you cannot formulate it as just this purely supervised problem, in the sense that a good summary is very dependent on the person. Like if you had told me what is Elmo or what is Bert, then for me it would have been like, oh, well, it's like Cove, but instead of machine translation as your objective function, you replaced it with language modeling, you trained it longer, and you made the model bigger. And then like that would have been a good explanation for me for what Elmo is. But if you didn't know what Cove is, you might not even know what a word vector is, then that is a completely useless summary, and you may need to make the summary even be longer than the original input document. So summarization is very context dependent, and the context is the person for whom you're summarizing that document. And so I think that is also something that we'll have to think about. How can you have better zero-shot training environments almost, and not just thinking of it as sort of standard data set with X inputs and Y as outputs.
Cool. I think Reza had a question.
Hey all, good to see you. Yeah, it's one avenue forward. If I put on my optimization hat, one avenue forward for these breakthroughs that seems like a pattern is taking concepts that we know from other areas in computer science and then softening them in order to have a model that can learn something new. Like in some ways, transformers are based on attention. Attention is like a soft lookup table. And then if you look at neural networks themselves, they have softened versions of all kinds of functions that we're used to seeing the disconnected hard versions of. So like we'll see step functions approximated as sigmoids and so on, right? So there's the extreme form of this is to take an entire Turing machine and soften it up so that it's differentiable. And that never went anywhere. Like there is a neural Turing machines paper, it died. But then every once in a while, we see really good success taking like a data structure and softening it up. So like, do we feel this is a good way forward? Maybe that's like a wealth of research areas right there where we look at what are some fancy data structures that we really like, soften them up, get a big data set, train it up. Maybe it'll push the boundaries somewhere. I feel like that's something that was perhaps the motivation behind the transformer. Jakob, who made it, I used to work with him at Google, and we used to have these conversations like 10 years ago. I wonder if that was part of his motivation for building that attention is all you need paper. I wonder if you guys see any of this in your research and your work. I think it's actually a really good way forward for a lot of model architectures, but willing to be told I'm wrong here. Yeah.
I mean, there are definitely some simple things like KD trees and stuff that will be really helpful for very fast lookups across like 1 million or 1 billion different thought vectors, if you will, for instance. So I can definitely see how we can be more inspired by other concepts and computer science.
Yeah, I definitely love the idea of taking explicit algorithms and using basically that inductive bias of what that algorithm should be doing, but that you insert weights sort of in there and soften it and get like differentiable renderers and differentiable particle filters and so on. Actually, Justin, you've had papers on this and as well. So I actually really like this trend that you would sort of take something explicit, soften it, and hang a few parameters in there and then optimize it end to end on some data set.
Yeah, I mean, first I'd like to push back on the idea that the neural Turing machine totally died. I think, there weren't direct follow-up papers that were called back, but it also used this kind of dot product lookup style attention that I think was pretty influential there and got used in later things like the transformer. But
yeah, exactly. It was NTM sort of like the first time we saw, I think, what looks like
I think so, because then it was like this key and the query and the value, right. And the NTM had that kind of mechanism, and that was I think that was the first time we saw it in that way. But speaking to the more larger point, I totally agree that softening algorithms is a super fruitful way to go. And as Andrej alluded to, one of the things that I've been super interested in the last couple of years is differential rendering, right? Because we've been doing computer vision a lot, and computer vision is input an image and output stuff about it. But we can take inspiration from computer graphics, which is kind of the opposite. And computer graphics is like input description of a scene and then output an image. But it turns out that we have computer programs that can input a description of a scene and output an image. And we can soften them in kind of ways that you were describing. And then we can build rendering algorithms that are themselves differentiable. And then once we've got a rendering algorithm that's differentiable, we can slot it in the middle of a neural network in all kinds of interesting ways.
Yeah, rendering is almost naturally differentiable, because typically to take a 3D scene, to bring it down to 2D, you have some matrix multiplies, and so it's sort of already kind of in your face that you could you could take the derivative of that. And it's really exciting to see the work there. One class of algorithms that I haven't seen softened that really feels like people should be working on is graph algorithms. They're near dear to my heart, but I don't think I'm biased unreasonably there. Like, I don't see a softened Dijkstra's algorithm. I don't see a softened breadth first search and a depth first search. I'm not sure what they would mean, really. Like, if you look at attention, it's quite different from a hash table, but if you really warp your mind, it's a softened hash table. So like a softened Dijkstra's algorithm, first you need to define it. Like, what does it mean? I have some candidate definitions there, but like, what do you guys think would be a really cool data structure to soften? Maybe I'm taking the conversation too far off field here. Feel free to just like have one of them, Russell, if you want to have a smaller conversation on this, but just one data structure that you think is the best candidate for softening right now.
That's a great question. I actually don't remember off the top of my head, but I think there was a pretty interesting paper on this in SysML, which is, a whole conference kind of at the intersection of systems and machine learning on, I believe it was B trees, kind of a neural network, deep learning inspired approximation of this, data structure that it has nice properties, right? In the sense that I think Andrej also covered this a bit in his Software 2.0 blog post, which is that, with this Software 2.0 machine learning inspired way of doing things, you get some really nice properties, right? Like deterministic runtimes. There's no branching. The computational units are very homogeneous, so it's easy to optimize with domain-specific hardware. You don't have to support, the full general possibility of kind of Turing-complete conditionals. And I think that there's a lot of opportunity for more and more systems and machine learning kind of tie-ins, but I don't necessarily have a favorite data structure in mind. Curious if others do.
We have to remember, by the way. Oh, sorry, go ahead, Richard.
I think on a somewhat related but also new note, I think we have to understand our biases here in terms of the kinds of tasks and data sets that we work on. and I'm actually quite excited to see a lot of the interest in different communities like deep learning Indaba and African communities and others to move into AI, because in many ways we're working often on problems that are sort of very interesting intellectually, but there are a lot of problems that are both interesting intellectually and could have more direct real life impact, like trying to predict where to plant the most trees to help climate change, or working on like things like the Ai Economist that you can apply to all kinds of interesting economic simulations and housing issues. And obviously like taxation is kind of interesting. 10 years ago, if you'd asked me if I'm interested in taxation, I would have been like, that sounds really, really boring. But now I'm like, well, I guess taxation is at the very core of social like inequality and productivity. And so I'm hopeful that as we think about more recent breakthroughs in AI, that we're actually starting to branch out a little bit and sort of come to terms with the fact that AI does have this real life impact now, and we have actually the possibility to make it more positive directly through the data sets, tasks, and simulations that we work on.
Do we have a question from Alexandra?
Yes, thank you so much for a fantastic discussion and for your time. So you have touched on transformers and particularly on GPT-3 models. So it seems like breakthroughs in those algorithmic spaces development are more rapid than, let's say, for explainable AI. And when it comes to such powerful models in terms of NLP and transformers, there are a lot of discussions around ethical and responsible AI. So what are your thoughts on advancing this area simultaneously as we go with our breakthroughs for data and model creation, and especially in unsupervised machine learning cases? I would be very interested to learn that. Thank you so much.
I think this is a super interesting question, and there's been a big tension kind of in the AI community of, how do we get kind of state-of-the-art numbers, right? How do we bump up the accuracy as much as possible? And then how do we actually understand, how these algorithms are working? And I think a lot of people point to, oh, well, people can explain their thinking. But I think it's really only true to first order, and that, no human could actually tell you, hey, here's all of the sequences of neurons that fired to let me do what I just did, or kind of decide what I just decided. And so the way I've thought about this is that in a sense, human explanation is itself a low dimensional approximation of our actual decision-making process. And I think the kind of quest for explainability in AI, it might be really hard to actually get to full interpretability ever, because the reality, the way we think and the way these models compute, it just is outside of the bandwidth of the human mind. But where I think the most progress kind of has yet to be made here, and where I'm personally very optimistic, is in these multimodal models. If you have language aligned with images, aligned with other data modalities, and a model that can, kind of take language in and use that as an input, I think it's not a huge stretch to be able to actually query that model in natural language itself and potentially get low dimensional approximations of the model's decision-making process, but in a format we can understand, right, which is language. So I haven't seen too much research on this, but that's something that I think is promising future direction.
I think the solution has to be kind of multimodal explanations too, because ultimately language isn't going to be that great at telling you, oh, it's because of these 3 pixels and this particular edge in this particular combination that the model identified this as a cat. So I think multimodal explanations could actually be a really interesting new research area that could potentially help a lot. And I agree that we should work more on explainability, and it is really hard. I think there's one way that you can, no matter how black box an algorithm is, improve the explainability. And that is by trying to find better ways to really identify which training samples were most relevant or related to the one you're currently trying to explain, and then understanding why this one was explained. So then even no matter how black box the algorithm is, if you can tie it back to its training data, you will have some explainability there. And then, of course, there are sort of there's a really interesting philosophical discussion that I can argue actually for both sides. You want if the dichotomy, which is a question, is not a given. The dichotomy is that you can have a more accurate model that's less explainable, or you have a less accurate model that's more explainable. And people say, oh, but important things like medicine, it needs to be explainable. And I'm like, really, I'd rather, like, if I have an algorithm and this algorithm saves 90 lives, kills 10, and I don't know why, this other algorithm kills 50 people instead of 10, and I know exactly why they're dead now. I don't know. It's tricky, because if in a litigious society, you might still have to go with the one that kills more people, but you have like a good cover for your organization. But really, ultimately, objectively speaking, it's better if you save more lives. And same with an average, you might make arguments. It's important financially, like if the algorithm makes financial decisions, it's important that you understand why it made this. But ultimately, you can easily come up with examples and say, well, you can either give the algorithm $1 million and get 2 million back, and you don't know how it did it, or you lose 500,000 of that, and you know exactly why you lost it and why it made its mistakes. It's a tricky bit, even in these heavy subject areas, to push. And so ultimately, I think, like Russell said, there are a lot of algorithms that where humans have a hard time saying, like, I use my muscles exactly in this way to move my steering wheel this far to the left. And there's a certain area of our brains that we don't have conscious access to either. At the same time, we can abstract a little bit better from it and still make some progress.
I was going to add a few points here if you don't. Oh, go ahead.
No, sorry, you go ahead.
Just on the explainability question. So for the most part, at least up until a year ago, most of the methods for explaining what a black box model is doing, we're looking at specific types or random perturbations of the inputs and then recording a change in the output as the primary way of probing these models. I think the multi-model approach is very promising. In fact, that brings me back to work a collaborator and I worked on in mapping these saliency maps typically produced by the perturbation-based methods into human interpretable attributes. But the blocker there is, of course, the access to attributes. So oftentimes data sets don't have that available. And then the question is, okay, what other modality can we refer to make this human interpretable? And then also another paper that came out from NeurIPS this year was investigating how humans respond to these explanations. They were offering a few different techniques. So the saliency map being one of them, mapping to natural language explanations was another. And then there was the one of explaining by example. And they have found that across the board for different tasks, humans mostly relate to explanations by example, which to me doesn't seem surprising because we're very good at interpreting analogies. So I think definitely looking at multimodal explanations and thinking about humans' perceptual reasoning is the next step in explainability literature.
Yeah, I was going to say that I'm at least very happy that there are a lot of workshops on explainability and a lot of papers that are coming out recently. There was on the dangers of stochastic pairs paper. There were papers that can leak the training sets of GPT and so on. And so a lot of unintuitive side effects of the use of these models, despite their obvious economic usefulness in some settings. And so to me, these models are just these new alien artifacts. And we're just it's like a child given a bazooka in some way. And I think it definitely is very important to really understand how these things are working. So to me, it's actually kind of shocking that stochastic, gradient descent and backpropagation could get us this far, and that the models are so powerful. But they definitely have a huge amount of unintuitive properties that need to be studied quite carefully. So yeah, really interesting. On
the one silver lining on this is that now that we can create these models that are getting in at least some small subsets closer to what humans might be able to do, they will be easier to study than at least the brain.
I wanted to ask a question back to Richard's point about explainability based on different training examples. So I don't know if folks remember this paper on influence functions from around 2017-ish, where basically the goal is to trace the model's predictions through the learning algorithm back to the training data and identify training points that were most responsible for a given prediction with directionality. That seemed to die down with that paper. I wonder if there's been follow-up work or if folks are aware of any other methods.
I'm not aware, unfortunately, but you're right. That would be very interesting, and is one of the ways to push further on that.
Yeah, I'm not aware of that paper, but I think this kind of related idea of differential privacy is also kind of exploded up. I mean, it's a little bit inverse in a way, right? Because the paper you're talking about, it's like you've got to train a model and you want to know which samples influence the model. I think differential privacy is more the idea that we don't want any one sample to have influenced the output of the model too much. So that, like, if I'm uploading my data for someone to train a big model on, I don't want my data to have been that important in the final outputs of the model. And that's a direction that's maybe a little bit orthogonal but related, and I think that's seen a lot of attention in recent years.
Shrey, did you have a question?
Yeah, hi. First of all, thanks for hosting this talk. It's been a really nice conversation. My question was, I guess, a little bit related to explainability, but more so on robust validation. So recently, there's been a lot of work that thinks about how to do validation of machine learning models, especially ones that are going to be deployed or going to be pushed to production in terms of, either CI/CD or looking at slice-based evaluations. I'm curious to hear your guys' opinion on this, especially since a lot of you people also work in industry, about how you think about knowing when a model is safe enough for critical slices of data, even if it's not explainable necessarily for those slices.
I would say the thing I've seen, even if you can't get explainability of the model's outputs, what you can do is be really thoughtful in your curation of the data set into interpretable subsets. So I think there's a tendency right now to measure a model's performance as an aggregate metric, whether it's mean average precision or what have you. But where I see the gap between academia and industry there is that in industry, people are increasingly measuring not just aggregate performance, but kind of curated unit tests almost, right? Of, hey, of the subset of my data that looks like this weird edge case, how did we do? Of the subset of my data that looks like that weird edge case, how do we do? And I think collectively there, you can still get an interpretable glimpse of where your model is doing well and where it's not doing well, even if you don't know exactly why.
Yeah, I think this is a super important topic, and I think it's not entirely a technical problem. I think in cases, so like in academia, we're often sort of playing around and our models are not really being deployed. But if you are deploying a model that's going to influence people's lives and make decisions for them, you have to think pretty carefully, I think, about who's going to be influenced by the decisions of this model. What are the potential harms and what are the potential benefits of the decisions of this model that it can have on different people? And is it affecting different groups of people in different ways, either disproportionately harming or disproportionately helping? And I think that's something we need to think about more as a social problem, whether to deploy big deep learning systems in the wild in different contexts.
Right. I think another one that I was going to mention just before was the idea of sensitivity analysis. You can take an input and then, for instance, change, if it's like a visual classifier, you can actually use computer graphics to change the color of the skin and see if there are different outputs or if the output changes, even though based on your changes, there should be an invariance. It shouldn't change. And so I think, similarly, you can give an overall data set to a model and then see if changing the zip code actually changes whether this person should get a loan or not in a banking environment. And then with that kind of sensitivity analysis, you can probably still analyze and see if remnants of redlining are still in that algorithm, and really it should not be using the zip code the way it is or at all. And so I think sensitivity analysis is kind of underexplored a little bit too, as a sort of more algorithmic way of trying to create invariance classes in your validation data sets and across different slices that would basically kind of move between different like protected categories and minorities that might not be as represented in the data.
It looks like we do have some more folks in the audience asking questions. Let's see. Vincent, did you have something you wanted to ask?
Hey, everyone. Yeah, I had a few questions, and I really love the direction that we're taking it here, especially some of the points around, how do we think about shifting developers' attention towards data set creation and curation, and love the focus on kind of focusing on specific slices of the data when it comes to monitoring and quality. So one of the questions that I have for you all is, one of the big themes that we think about here at Snorkel is this idea that, what is the right IDE or software engineering interface when it comes to providing domain experts, not just data scientists, right, the right tools to program their data sets and models. And there's a lot to learn from, say, doctors or fraud analysts or legal analysts who are engaging in the actual development process of building AI applications. And I'm wondering, from both an industrial and kind of academic perspective, how are we thinking about incorporating these experts into the software engineering process in what I guess Andrej calls software 2.0?
Yeah, I guess yeah, I think, well, I had a blog post on this pretty early. I suppose the software 2.0 blog post, basically when it really hit me at Tesla, that I was doing a lot of data set curation, and that was kind of like the way to get everything working. Really, you're trying to program a system, and your system now is like a neural net. So how do you program a neural net? Well, it has a certain functionality in certain cases, and then how do you really influence it? It's all through curation of data sets. And of course, you can change the architecture, and you have a few knobs there and on the training system itself. But really, most of the programming really is in a curation of these data sets. So really, it was a bit of a call to action for the community to think through tooling to help us curate these data sets and what that looks like. And so, Scale, of course, there's a lot of work here. We do at Tesla, and I'm seeing increasingly more tools and startups in the space. And we've internally come up with a lot of workflows for, discovering which examples are worth labeling, and how do you even quantify the bang for the buck, because you're in this new regime that is not typically studied in academia, where I could, in principle, label any example, and I just don't know which examples to label and which ones give me the most bang for the buck. How do I identify them, and so on. And so it's a very different setting that I think is really hard to study in an academic setting. Yeah, we sort of have our own internal answers to a lot of these questions at Tesla, of course, but I'm kind of curious what this will look like when the dust settles across the community. Yeah, I think it's still evolving.
What's really interesting about that is that I think we're at this phase now where kind of some of the largest and most sophisticated kind of AI using companies have basically had to build out that internal tooling themselves, right? Like Tesla has for really high quality data set curation management, answering the question of what unlabeled data should I send for labeling next? All this type of stuff that in practice just has much more impact on your downstream performance than any modeling changes. And yeah, shameless plug. This is exactly what I'm working on now at Scale, which is this product Nucleus, trying to be that kind of data set IDE for all of the other companies and individuals out there that don't have a giant internal tools team to build it themselves. And I think the thing that a lot of academic research in data set curation and active learning and so on misses is that it doesn't need to be fully automatic, right? Like you can inject human judgment in saying, hey, I noticed we're having a lot of failures when one lane forks into 3 lanes. That's a really tricky edge case. Can we source more data that specifically looks like that? And it looks like those failures are maybe actually caused because we had an ambiguous annotation instruction for that edge case. Let's go fix the annotation instructions and get that part of the data set cleaned up. I think that's where the tooling basically has the opportunity to really accelerate the end production ML success.
I just wanted to say this idea of, we've got infinite data, we don't know which points to label. That's called active learning. There's hundreds of papers on that, but we all forgot about papers more than 5 years ago. But apart from that, like I think it's just I think we have to change how we think about machine learning a little bit if we want to make progress on this space. Because a lot of people, at least in academic machine learning, are thinking, we've got this data set, how do I get a high score on this well-known data set? But we need to reframe a little bit and think like, I'm a person and I want to solve a new problem with machine learning. And how can I effectively solve that problem as quickly as possible? And as an entire workflow, not just training the model. And I think we need to look a little bit outside machine learning to human-computer interaction and other areas of computer science to think about how to study that.
Quick announcement. So we'll go on for about 10 more minutes here and try to wrap up by 9:30. Thanks everyone for all the questions so far. It's been awesome. Emily, did you have something to add?
I'm Emily, and first of all, I would like to thank all of you that offering me the chance to talk. So actually, unlike most of you, and I'm from psychometric field, which is more related to the educational measurement and the statistics. So why I'm here, it is because I noticed that many of you guys come to my field as a researcher or scholar. So for example, recently I read an article. Some of you guys use our psychometric models in machine learning. So for example, normally when I talk about the psychometrics, we have our own models. Traditional ones like CTT, classic testing theory, and a little bit more advanced one, which is item response theory based one, and or a more advanced one or highly advanced one, which is the diagnostic classification. Thank you very much, though. I mean, especially from Richard and Maria. So, because you say it is possible for us to have a multi-model validation to understand the accuracy for the prediction purposes. So my question was, it is possible to make it true or vice versa to be true, to let us to integrate your machine learning algorithm to our field. So what do you think of it? Because basically, I'm reviewing articles in the past few weeks, and then which is kind of a new topic in my field, even though I know many of the psychometricians, they try to use the machine techniques. So as like you have mentioned, like artificial neural network or forest tree, etc., to predict accuracy. And also you have mentioned that. So probably machine learning algorithm can have a better or more accurate predictions regarding to the outcomes. But because since we have our specific models, so I think our results will be more interpretable or can have a interpretable ability that the parents or decision make the parents, they would like to hear, because if you mention machine learning to them, they have no idea for what you're talking about. But if you have our models, so they will know, oh, okay, so I know where my kids are at, so what my kids are good at, so specifically what attributes they know well and what other attributes they don't know very well. So my question is that, is it possible for us to come to your field to use your machine learning algorithm to our models and then to integrate that to have item response theory modeled machine learning algorithm? And then I don't know if it works. So I'm kind of confused though. Thank you very much.
So I guess I can't speak for all of our community, but I think there are definitely some interesting ways that one could study, for instance, how when students try to learn multiple different tasks, how they can interfere with one another, for instance. And I think neuroscientists will be interested and are interested in are studying sometimes how these deep learning and AI models, how much they can correlate with human behavior and the human brain or primate brains. So we know, for instance, like the visual cortex has a lot of neurons that are very similar to some of the neurons in convolutional neural networks and so on. But I think that's sort of just my 2 cents on that question.
Thank you very much, Richard. So,
as a speaker, My question relates to, and thank you for making this room, by the way, this is brilliant. My question relates to sort of like the reemergent tendency to view symbolism as a necessary add-on to deep learning for a complete AGI system. And we have been having several rooms here, and there were a lot of discussions around it. One of the ideas, and I've been thinking deeply about this, for example, we have this GPT-3 large transformer model, and we know that it can, to a certain extent, and better in the future, it can write computer code from natural language. Let's just, for example, say Python. And we know that GPT-3 can do up to, I believe, 3-digit by 3-digit arithmetic operations pretty well, but the performance subsides after that. So that being said, and given the example of, for example, as a human natural intelligence, I struggle with 3-digit arithmetic operations. But since I can have a rule about it, I can try to apply that rule in my mind or on paper. I can do any digit operations given enough time. And I can also code some Python code and let the computer run it. So bringing it all together, my question is, since GPT-3 can turn natural language into code at some efficiency, why not allow GPT-3 to create the code, let's say in Python, and store it in an external memory, and anytime it is presented with this arithmetic operation, relegate the processing to the CPU? Would that just be against the idea of creating an AGI system inherently? I hope I was able to make my point clear.
It's definitely an idea that's very interesting and that people explore in sort of sequence to SQL. For instance, there's a paper we published a couple of years ago as one of the first data sets of having code, having natural language, and then having SQL code on the other side, so that sometimes you would know the only way to answer a question is by actually running a SQL line of code across a massive database in order to be able to answer that question. And I do think there's it's not explored enough yet of how you can reach higher levels of intelligence by combining the way we would think it should be done in an end-to-end learnable model versus adding these inductive biases like, oh, you should be able to program, you should be able to have access to an external memory database, and so on. It's definitely interesting. The problem is that it's very hard to train, and the objectives on getting there are very unclear. And if it was as easy as like, oh, you see millions of programs, and hence you know how to write a new program even for a completely new environment, and then knowing when to store it and when to trigger it and when to make it a soft version like we discussed just before. I mean, these are all like unanswered questions, but it's definitely another interesting space to explore.
Yeah, I think the question is barking up like a very interesting tree. I was kind of thinking about what it would take, like what it would look like if you were to give a calculator to GPT, for example, and then GPT has to sort of use this external interface through some API, so it can sort of emit input to this block module and get a output out of it and use it somehow in its objective. So it's not really clear how that's set up, but I think it would be really interesting to basically give it modules that have different inductive biases and have it sort of learn to use them as tools, or like say a scratchpad where it could as a human, for example, I don't do arithmetic in my mind. It's really hard. I take a pen and paper and I sort of work out the addition problem. And I do that by using the paper as a form of like a memory, I suppose. And so we need some kind of equivalent of that, I think, instead of using just the channels of the arc. Yeah.
So write it themselves, then know when to store it to memory, and then re-trigger those sub-functions, and then compositionally combine them with fuzzy reason. I mean, honestly, one of the big questions is how to combine fuzzy sort of probabilistic statistical reasoning with very discrete logical reasoning, and I think that's one of the big open questions towards AGI that nobody has really, I think, in a principled way solved or even tackled yet.
Yeah, I was really interested in this area a few years ago, and I was working on this idea of neural module networks, where you have a neural network that learns all these independent chunks that are all neural networks that are meant to specialize to different functions. Like maybe you've got one module that's good at recognizing objects, one module that's good at counting objects, one module that's good at performing logical filtering operations. And then you have a system that inputs a question and then converts the question into an arrangement of the modules in the right way that would cause them to answer the question. So I had a paper about this a couple of years ago that I was pretty excited about at the time. But as Richard alluded to, the really hard part is getting these things to train, because neural networks are really good at neural networks are continuous optimization. We're pretty good at continuous optimization. But anytime you move to these discrete or logical representations, you're moving into combinatorial optimization. And that's just not something we really know how to do very well today.
Awesome. Super great final question to end it on. And thanks everyone so much for coming. Really interesting conversation. Yeah, hopefully we get to do it again soon. And for folks who want to keep talking about AI, I'm actually scheduled to go in another room with some other folks on the future of AI next, if people want to join. Otherwise,
Oh, wow.
Let's do it again soon. And yeah, thanks everyone for joining.
Thanks everyone. Have a wonderful evening. Bye-bye.
Thank you.
Thanks, everyone. Yep, thanks, bye.